Hey everybody, Dr. A here, and in this video we're going to be exploring an example of using Castigliano's method for a beam analysis. And in particular, what we're being asked to do is to find the slope angle and vertical displacement at point B using Castigliano's method, of course, and then check the results with pre-derived formula, or formulae is one plural way of saying formulas. EI is constant. So here we have a cantilever beam. We have a fixed connection at A, and we have a free connection at B. It's 2 meters long, and we have a point load of 3 kilonewtons at the free end. So one thing we can do to kind of help us visualize what's going on is I'm going to go ahead and just sketch the shape of the elastic curve. And let me make that look a little bit better for us. So what this looks like is a concave down curve, and at point A, in the vicinity of point A, we have this kind of taper here because there's no deflection or rotation at point A. And so what we're looking for is this vertical displacement. We're going to call this delta B, and then what we're also looking for is the slope of this slope angle, theta B. So I'm going to put a tangent line here, and what we're looking for is theta B here. Okay, so let's go ahead and get started using Castigliano's method. All right, so under solution, the first thing I'm going to do is I'm going to define an x coordinate. Okay, define an x coordinate. All right, and I'm going to do that just to because one wasn't defined for me. So probably the easiest thing to do is define our x coordinate to look kind of like this. Here's our 3 kilonewtons, and how about we define our x coordinate as pointing to the left is positive. Okay, and then this is 2 meters long, of course. All right, now the next thing we're going to do is go ahead and figure out which one of these we want to calculate first, because really this is kind of like two problems disguised as one. Let's go ahead and start with the slope. Okay, so I'm going to say let's start with theta B. Okay, and so what do? Well, we place a variable couple moment M prime at point B. Now, as we said in our previous video, we're going to place this variable couple moment on point B with the real load of 3 kilonewtons. Okay, so here's what I'm going to do. I'm going to redraw this system. Okay, draw this a little bit better for us. There's the 3 kilonewtons, okay? And I'm going to place this variable couple moment just like this, M prime, okay, with the real load. And of course, this thing is 2 meters long, all right? And if we want to include our x coordinate on here, it looks just like that, all right? Now what I'm going to do is use method of sections and develop the internal moment function. So by method of sections, here's what I'm going to have. I'm going to come over here on the right side of my screen, and I'm going to make a cut section here. And I've got the 3 kilonewtons here. I'm going to try to color coordinate for us. Here is M prime. And what distance am I cutting here? Well, this is just a distance x, all right? And then what becomes visible when I make this cut? Well, I'm going to have an internal moment function, M, okay? Now, I'm also going to have an internal shear function, but for Castigliano's method, I'm not really interested in that. I'm just interested in that internal moment function, M, all right? And so I'm going to say sum of the moments about the cut equals 0, counterclockwise positive, all right? And I'm going to say minus M, okay? That's this guy right here, the internal moment. And then I'm going to say minus 3 kilonewtons times x, and then I'm also going to say minus M prime equals 0. All right. Now remember, this M prime, that is the applied variable couple moment, and it's there. It's in our free body diagram, so it shows up in our equilibrium equations. We do a little bit of rearranging, and we solve for m, and we're going to get negative 3x minus m prime. All right, so that's really our only moment function, right? Because we only have one domain and we don't have any other abrupt changes here. So now I can go ahead and get that partial derivative. I can say dm prime. So what is that? Well, it's the partial derivative of this function with respect to m prime. So I'm treating m prime as the variable, as the mathematical variable, which means that my partial derivative is just -1, right? Because the 3x term is treated like a constant when I'm taking this partial derivative, all right? What do I do next? Well, I'm almost done. This is a pretty short process, okay? So now I'm going to say theta sub b equals the integral from 0 to L m dm prime 1 over EI, of course, dx, okay? Only one segment, only one domain, so we don't need the summation here, all right? And now I'm going to make a note here, and we saw this in the previous video. We're going to say set m prime equal to 0 in the moment function when we evaluate this integral. So finally, I'm going to get theta b equals the integral from 0 to 2 meters, and m is going to be negative 3x. dm prime is -1, and of course we have the 1 over EI. And then we have a dx right here, okay? Now this is a pretty easy integral, okay? So you could probably just easily do this by hand. Let's see, we should get 1.5 x squared evaluated from 0 to 2 meters. And when we crank this through, let's see, 2 times 2 is 4. 4 times 1.5. So I think we get 2.5. Oh, sorry. 4 times 1.5. 6, I'm sorry. I hit the minus sign instead of the multiplication sign of my calculator. We get 6 over EI. Okay, now what are the units of that numerator of 6? Okay, well, let's think about it. We've put a variable couple moment there. We've taken an integral of some different terms here. So let's think about how these units come out. Well, this 3x minus m prime, this is where the moment function is, that carries units of what? This carries units of kilonewton meters, okay? What about this -1 here? This is going to be unitless, okay? And so the dx then carries units of meters. And so the units of my numerator should be kilonewton times meters squared, okay? Does that make sense to us? Well, it should, okay? If you substitute in values for E and I, if we had values for E and I, then we would end up getting a unitless final number if we substituted in values for E and I, because, you know, it should ultimately collectively have units of radians, okay? And so this is going to be a clockwise rotation. So that's one of my answers, all right? Let's check this with a pre-derived formula, all right? So I'm going to change colors here again. I'm going to say from a pre-derived formula, we can write theta b equals PL squared over 2EI. Okay, and this is from a just any kind of pre-derived formula from a textbook. And so this would be 3 kilonewtons times 2 meters squared over 2EI. And so, of course, we end up with 6 kilonewton meters squared over EI, and that would be rotating clockwise. So this is just a way to check ourselves, make sure we're checking things off correctly with Castigliano's method. All right, that's half of the problem, all right? The problem asked for something else. The problem also asked for what? It asked for the vertical displacement, right? The vertical displacement at point B. So what do we do for that? All right, let's now compute vertical displacement. All right, and so here we draw this free body diagram, and we're going to say P plus 3 kilonewtons, okay? And this is 2 meters long, all right? Now, we keep the real load on there. That 3 kilonewtons is the real load, and then we put a P on top of it. That's the variable load, all right? And so I'm going to define the same x coordinate that I saw before. So this process is quite similar. I'm going to use method of sections, and I'm going to have P plus 3 kilonewtons here. I have a distance x here, and I have an internal moment m, and I also have that internal shear force v that I'm not really interested in. So I'm going to say sum of the moments about the cut equals 0, counterclockwise is positive, and I'm going to have minus m minus the quantity p plus 3 kilonewtons times x equals 0. All right, and you can do some rearranging and repackage this algebra however you want to. You could say, minus px minus 3x if you want to. All I did was I distributed this negative sign and this x value, okay? Now we can compute that partial derivative dm dp, all right? And how does this work out? Well, I end up with negative x as my partial derivative. How do I know that? Well, the 3x term is treated like a constant when I'm taking the derivative with respect to p, and then the quote constant term that's attached to p is the negative x. All right, so that's your partial derivative operation. And now what I'm going to do is calculate delta b. All right, and I'm going to say delta b equals the integral from 0 to L, and this is going to be the moment function dm dp, and of course 1 over ei is there, dx, and then we're going to also make that note, set p equal to 0 in the moment function and the integral because it's not really there, all right? And then we're going to say delta b is the integral from 0 to 2 meters of negative 3x times negative x, 1 over ei dx. And this is kind of also an easy integral to compute. When you multiply these together, you get 3x squared, raise to the power divided by the new power. So we should just end up with x cubed over ei evaluated from 0 to 2 meters. And what do we end up with here? We end up with 2 cubed is 8. You get kilonewton meter cubed over EI, and it is deflecting downward. Let's check the units on this. So the 3x has units of kilonewton meters. The negative x is going to have units of meters, and the dx also has units of meters, so that's where we get the kilonewton meter cubed. Now let's check this with a pre-derived formula, okay? Pre-derived formula. So from a pre-derived formula from any textbook, any structural analysis or mechanics materials textbook, you'll get delta B is PL cubed over 3EI. And so that would be 3 kilonewtons times 2 meters cubed over 3EI. And so you end up with 8 kilonewton meter cubed over EI deflecting down, okay? So that's it. That concludes this example video of how to use Castigliano's method, and we double checked it with some pre-derived formulas to make sure we're getting consistent values. I hope you found this video helpful. Please hit like and subscribe and be on the lookout for more content like this. Thanks for watching.